Hey team, welcome to the first video on the binomial distribution. I'm going to be doing a few of these, or maybe just do them all in one go. I think I'm just going to do them all in one go. Okay, so this could be the first and last video on binomial distribution. Okay, so again, in these videos, it's just me getting straight to the application. I won't be getting into any of the theory. So that was done in class, so make sure you study your class notes. All right, let's begin. So X is binomially distributed with 6 trials and a probability of success equal to 1/5 at each attempt. What is the probability of exactly 4 successes? Right, so we've been told X is binomially distributed. We can use a calculator, by the way, so I'll show 2 methods. X is binomially distributed, so X tilde B. Now, the first number in here is the number of trials, so 6, and the second one is, you can either use a fraction or a decimal, it doesn't really matter, is the probability of your success. All right, now, part A wants exactly 4 successes, so we want the probability that X, big X, equals 4. We want exactly 4 successes. Now, working out, I will just write the formula. So it's NCR, so we have 6 trials, CR is our number of successes, so 6C4, times P, probability of success to the power of the number of successes, times the probability of failure, which would be 4/5 in this case, because P and Q, success plus failure, have to add to 1, to the number of failures. So if there's 4 successes out of 6 trials, there must be 2 failures. Now, we're going to approximate this to 4 decimal places. So, you can go NCR 6/4, so that's 6C4, okay, times 1/5 to the power of 4, times 4/5 to the power of 2, and we should get that, if we approximate that to a decimal, number convert to decimal, 0.0154. Now, alternatively, we go into probability distributions. All right, binomial PDF, because we want X to equal exactly 4. Number of trials is 6. Probability of success is 1/5, and we want X value to equal 4. Same answer. Okay, so just go back and replay this if you didn't quite get all of that. Let's continue. So B, we want at least 1 success. So probability of X being greater than or equal to 1. So that's 1 success. And, all right, so I'm thinking I'm just explaining this a lot completely. So this means we want the probability that X equals 1 plus the probability that X equals 2. Get what I'm doing? All right, plus blah, blah, blah. All right, so 3, 4, 5, and also X equal to 6. So that would be the longest way we can go about doing it, most comprehensive way. But since all our probabilities have to add to 1, we can also do this. Because we see that, oh, what value of X is missing in all these? 0. Because we can have no successes as well, right? So if we do 1 minus the probability that X equals 0, that should give us, that answer would still give us the same value as if we did, X equals 1 plus X equals 2 plus probability X equals 3 all the way up to probability X equals 6. So what we can do is working out, this is the quicker way to show it. So 1 minus NCR P to the power of R Q to the power of, R would be 0, to the power of n minus r, so 6 minus 0 would be 6 in this case. So that would approximately be equal to 1 take NCR 60 times 1/5 to the power of 0, which is 1, times 4/5 to the power of 6 is that thing, but we want to convert to a decimal, 0.7379. 7379. Okay, calculator method. So this time we go into probability distributions CDF because we want more than one value of x. So number of trials is still 6, probability is still 1/5 of success. Our lower bound is 1 because we're starting at x equals 1 and we're going and we want to add all the probabilities up to x equals 6. So that's our upper bound. Press OK, same answer. All right. And finally, let's do C. 3 or fewer successes. So this time we want probability that x is less than or equal to 3. All right, so that equals. Okay, so I'll notate it in a variety of ways, and you can choose which one you want to use, right? But if it's a calculator, at the end of the day, you're going to have to just type it into your calculator anyway, so you might as well pick the shortest way or the quickest way. So we have probability that x is less than or equal to 3 will equal the probability that x is 0, probability that x is 1, plus probability that x is 2, plus probability that, oops, I'm going to run in space, not really, alright, there we go. Alright, or we can do 1 minus the probability that x equals 4, minus the probability that x equals 5, minus the probability that x equals 6. Now either way, if we want to write the formula out, it's going to be a bit long, so since we can use a calculator, I'm just going to use the calculator function to help me get this, because we'll all get the same answer anyway. So distributions, binomial CDF, 6, 1/5. Alright, our lower bound is 0 because 3 or less, and we're going up to 3 because we want to include 3. There we go, 0.9830 approximately. Alright, so that's example 4. So that's kind of like an introduction into a bit of the nitty-gritty. Alright, let's go on to the next example. So example 5. Alright, let's make some space here. Okay, so the probability that I get on a bus to work, well, get a bus to work on any morning is 0.4. What is the probability that in a working week of 5 days I will get a bus only twice? So, okay, so let's go through the checklist of conditions for a binomial distribution, right? So, is there a discrete number of trials? So 5 days. Yes, we do. All right, n is 5. So, and do we have 2 options, success or failure? Well, we actually do. So getting a bus would be success. Not getting a bus would be the failure. So this, and we're going to assume it's independent, right? Because it says the probability that I get a bus to work on any morning is 0.4. So that's kind of just suggesting this is independent. So let's use, assuming this is a binomial distribution. We have 5 trials and the probability of success is 0.4. Alright, we want to find the probability that we get the bus, well, this person gets the bus only twice, so that means x equals exactly 2. So this becomes NCR 5C2 P to the power of R, so 0.4 to the power of 2, and then Q to the power of n minus R, so 0.6 to the power of 3. And then type this in, NCR 52 times 0.4 to the power of 2 times 0.6 to the power of 3 equals 0.3456. If you use the distribution function to do this, you'll get the exact same answer. So whichever way is fine. Okay. Let's do example 6. When administering a drug, it is known that 80% of people using it were cured. The testing program administered the drug to 2 groups of 10 patients. What is the probability that all 10 patients were cured in both groups? Okay, so we did discuss this in class. Can we just do 20 patients? In this case, I think we found out that we could, but for the sake of showing the method, I'll treat this as 2 separate groups and multiply the 2 probabilities together. Alright, because we want 10 people in the first group to all be cured and 10 people in the second group to all be cured. So if we want to find the total probability, we have to multiply that. This is an AND situation, and we multiply. All right, so let's say, okay, so again, assuming this is a binomial distribution, we have number of trial would be 10 because I'm only doing one group at a time, or just one group, and our probability of success is 80%. So we want probability of x equals 10. So how I guess we can just set it out right from the beginning is we want this. Okay, because we want both groups to both have 10 patients cured, and we want the combined probability, so it's multiply. So, which basically means this is probability of x equals 10 all squared, right? And then we just apply the formula and figure out the answer. So this is NCR, so 10C10. We have P to the power of R, so 0.8 to the power of 10, and Q to the power of N minus R, or the number of failures, which is going to be 0. Alright, and then we're going to square that. So we can actually just do this in one go if we want to. Bracket NCR 1010 0.8 to the power of 10 times 0.2 to the power of 0 all squared, okay, which is 0.0115. So about 1.15%, which is quite low. Which kind of makes sense. Even though it's like an 80% cure rate, we want every single person to be cured, so it wouldn't be that likely. Okay, let's keep going. Alright, example 7. Okay, a box contains a large number of carnations, which 1/4 are red, the rest are white. Carnations are picked at random from the box. How many flowers must be picked so that the probability that there is at least one red carnation among them is greater than 0.95? Alright, so show you, thinking whether I show 2 methods here or not. Okay, maybe I do show both methods. So the first method, we'll try to do as much as we can by hand using formulas, because at the end of the day you will have to use the calculator to solve this at some stage, alright, because we're solving for a power. So in this question, the number of trials is missing, so it wants you to figure out the number of trials you need. Alright, so the probability that x is at least 1 is 0.95 or greater. Wait, is greater than 0.95, right? So assuming this is a binomial distribution, because let's just do that for this whole exercise, because that's what we're dealing with. We have n number of trials, which we don't know, but we know that we're trying to get red carnations, right? So 1/4 P is our probability of success, which is 1/4. Alright, we want the probability that x is greater than or equal to 1 is greater than 95%. Alright, so what we can do is if we solve, so if we let if we solve this equation, alright, it will give us a number of trials in n for which the probability is exactly 0.95, and that'll probably be a decimal, so we would round up, right? Because we can't have, you know, a like part number amount of trials, right? It has to be a whole number. All right, so p, the probability of x is that x is greater than or equal to 1. That's the same as saying 1 minus the probability that x equals 0. All right, because we want everything from 1 to whatever, okay? So the only number we're not including in that range is 0. All right, so let's just solve this. Let's see how we go. So this is going to be NC0 times probability of success to the power of 0 times probability of failure to the power of n, which equals 0.95. All right, now this is more of a conceptual thing, but anything C0, so NC0, like whatever n is, it's going to be 1. So, and then 1/4 to the power of 0, that's also 1. So we're actually left with 3/4 to the power of n should equal 0.95. And then if we just isolate 3/4 to the n, we'll get 0.05. And then see how you still have to use a calculator here. So if we like log or ln, it doesn't matter, but if we ln both sides, we can use log laws to isolate n. And let's do this. Rearrange. N approximately equals ln 0.05 over ln 3/4, 10.41. So that means if we do 10.41 trials, we'll get exactly 95% of picking at least one red carnation. But we can't have 10.41 trials, and we need to have at least a 95% chance, so we have to round up. So therefore, n equals 11. All right, so that's how you can do this by, like, algebraically. I wouldn't say completely by hand, because you do need to solve using a calculator. I guess I'll do a guess and check method, and this is all would be calc. All right, I would suggest you probably just understand that method I just did. But okay, so let's do, you know, so I'll just do it quickly. So let's say you let n equal 0, then the probability of this would be guess and check method on calc. So this, then you would just go in the calculator and just be like, probability, distributions. Now you want at least one red carnation, so it's CDF. So you're seeing what happens if you put n equals 10. You're trialing it. The probability was what? Quarter, 0.25. Your lower bound is 1, and your upper bound would now be 10 because you have 10 trials. You want at least one, so it's 1 to 10. Okay, and see how that's what, approximately 0.9437. All right, so that's not 95%, so it can't be 10. Now that's pretty close though, so you wouldn't, in your next attempt, you would just go up 1 and see what happens. So let's let n equals 11. CDF here, so 11, 0.25, 1, 11. See how it's greater than 95%? Then px greater than or equal to 1 approximately equals to 0.05. 0.9578. All right, which is greater than 95%. So therefore, n equals 11. So at the end of the day, 11 flowers must be picked. All right, that's a very good one to help your understanding of how to apply this concept and formula. All right, let's keep going. Almost there. Okay. This one, I think everyone found this quite easy. So I'll just do this one quickly. Bias dice is thrown 30 times and the number of sixes seen is 8. The dice is then thrown a further 12 times. Find the expected number of sixes for these 12 throws. Alright, so this is basically let's make this a binomial distribution where the number of trials is 12, right? Because we're then throwing the dice 12 times, but the probability of success we're going to derive from the actual experiment. So we saw 8 sixes out of 30 times, right? So that would be our probability of success. Now, the expected number, even intuitively, you would just think to do 12 times 8 over 30, which is n times p, which is literally the formula, which is 12 times 8 over 30, which is 3.2. Okay, that's it, done. So that's expected value, quite straightforward. And G, this is the last exercise for the binomial distribution because I think then it's normal. Yeah, so let's just finish and do everything in one video. In a large company, okay, so this talks about, this one's got expected value and variance. All right, so the variance formula is just NPQ, so nothing too crazy there. So assuming, again, this is a binomial distribution, a random sample of 15 is selected, so 15 workers, that's our n, number of trials. So P probability of success would be travel to work on public transport, which is 0.4, 40%. All right, find the expected number of workers. So expected number of workers would be NP, which is 15 times 0.4, which is 6. Now, it wants the standard deviation. Remember, that's just the square root of the variance. So we actually need to find variance first. So you can either write variance bracket capital X, or you can write sigma squared. Either way. All right, so that's NPQ, which equals, well, NP is 6. Well, I'll just write the whole thing. So 15 times 0.4. Now, if P is 0.4, Q is 0.6, right? So that should equal 6 times 0.6 is 3.6. All right, but now we want the standard deviation, which is just sigma. So we need to square root that. And standard deviation, we don't want the negative value. So square root 3.6 is 1.897, so 1.9 approximately. 3 sig figs would be, yeah, 1.90. Okay, and that's it for binomial distribution. The rest is you practicing how to apply them and just applying the concepts. So thanks for watching, and I'll see you in the next one where we do normal distribution.